So far, we've seen how we can add two vectors. You take a vector, think of it as an arrow, adding it to another vector amounts to completing the parallelogram. So if this is vector A and this is vector B, this becomes A plus B. And we've also seen, for example, if I take a vector A and I multiply it by a scalar 2, basically it just points in the same direction and it's twice as long, right? So these are some of the operations we have seen. But what about the next natural operation, which is if I take a vector A and I take another vector B, and my question is multiply. What would that look like? How can I multiply an arrow with another arrow? Right, that's the question is sort of difficult to answer because multiplication is not very well defined in this case. There's no intuitive way in which this can be done. So it turns out there's going to be two different ways in which we can take products for vectors. And the first is called the dot product. Okay, so we'll just start with the definition here. So given vector A, suppose the components are A1, A2, A3, and a vector B whose components are B1, B2, B3 in the X, Y, and Z direction, then the dot product of A and B is the number. So what that means is this is a scalar quantity. So this is a particular kind of product of two vectors, which does not give us a vector. It gives us a number, it gives us a scalar quantity. Is the number, which is written as, so dot product, as the name says, we write this product as dot. Right? So A dot B is the number. How do we obtain this number? We multiply each of the components and then add them all together. Okay, so it's never going to be a vector quantity. It's always going to be a scalar quantity. So for example, if I have a vector this and I dot this with this, then I take the first numbers, multiply them. I take the second numbers, multiply them. I take the third numbers, multiply them, and add all of them up. So negative 6 plus 14 plus 0 equals 8. So the dot product of these two vectors is 8. The same thing can also be written in a different notation. So I could have I plus 2j minus 3k multiplied by 2j minus k. And I will do the same thing. I will take the I components, which is 1 here and none here, so 0. I will take the j components, then I will take the k components, multiply each with their respective values, and then add them up. Oh, sorry, 3 times 1 is 3. So this comes out to be 7. So remember, it's not a vector. What it gives us is a number. It gives us a scalar. We will see what that scalar quantity represents in a little bit. Let's look at some properties of the dot product. So what is the setup? Let A, B, C be vectors. And lambda is a scalar, right? Which means it's a real number, just a regular old real number. Some properties, if I dot a with itself, what I really get is the square of its magnitude, because what is that going to be? It's going to be component I squared plus component j squared plus component k squared, which is exactly the square of the magnitude of the vectors. Second thing, if I dot a with b, it's the same as if I dot b with a. It means it is commutative and order does not matter. Again, makes sense. You can justify the reasoning to yourself. If I dot with the addition of vectors, I can just distribute. So this works similar to regular multiplication of real numbers that you've seen, right? It just distributes properly. The next one is, if I scale one vector and then take the dot product, that will be the same as just scaling the dot product, which will also be the same as. So once again, it's similar to a regular multiplication that you know. So nothing bad happens. If I take the 0 vector and I dot it with any vector, I will get the 0 vector. Not the vector. I will get 0, because then it's going to be 0 times whatever the I component of A plus 0 times whatever j component of A, and then 0 times k component of A, all of which add up to give 0. Okay, now geometric interpretation, right? So geometrically is where this becomes interesting as to what A dot B is. So there's a theorem, and it says if theta is the angle between the vector A and B, then A dot B, this dot product, equals magnitude of A multiplied by magnitude of B multiplied by cosine of theta. Okay, and as a result of this, we also have a corollary, which is if theta is the angle between two vectors A and B, we can find theta, because cosine theta from the equation above is going to be their dot products divided by the magnitudes. And a very nice result here is that if A dot B equals 0, it means cosine theta is 0. It means theta is pi over 2 radians or 90 degrees. And the vectors A and B are orthogonal. What does that mean? It means they are perpendicular to each other. So dot product gives us this really nice characterization of vectors, which means that if I take the dot product of two vectors and it comes out to be 0, it tells me that the angle between them is 0, right? And a consequence of this is that dot products tell us about the relative orientation of two vectors. That is, they have something to do with angles. And we're going to utilize that in order to define something called direction angles and direction cosines, which will be useful later when we learn more about equations of lines and planes in 3 dimension. So this video ends here. We'll continue the discussion on using dot products to understand relative orientation in the next video.